Welcome to my channel Sharath NEET Academy. If you like the concepts, you please subscribe and press the bell icon so that you will get notifications quickly, and also you share these links with your friends. Okay, in this video we are going to discuss about the concept of magnetic field produced by a current carrying circular loop. Before that, see, when a charged particle is in motion, it produces electric field and magnetic field. But due to charge, how much magnetic field does it produces? That we haven't calculated. Whereas a current carrying conductor produces magnetic field around it, but we are able to calculate magnetic field at any point due to this straight conductor. Magnetic field is mu naught by 4 pi I by R into sin alpha plus sin beta. We have tried to calculate magnetic field due to current carrying conductor, but whereas magnetic field produced by a charge is not determined. We are not determined because, for example, when charge is moving in this side, if I would like to calculate magnetic field at this particular point, see, when charge is here, magnetic field is certain value will be there. As it moves away from this point. That means at this particular point, magnetic field is keep on changes. Magnetic field at this point is a variable. So that's why we are not able to calculate magnetic field at any point due to moving charge. Now current carrying conductor ge magnetic field na calculate ಮಾಡಿದೀವಿ. ಆದರೆ ಮೂವಿಂಗ್ ಚಾರ್ಜ್ಗೆ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಪ್ರೊಡ್ಯೂಸ್ ಮಾಡುತ್ತೆ ಅಂತ ಮಾತ್ರನೇ ಹೇಳಿದ್ವಿ. ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಒಂದು ಪಾಯಿಂಟ್ ಹತ್ರ ಕಂಡಿಡಿಯೋಕ್ಕೆ ಹೋಗಿಲ್ಲ. ಯಾಕೆ ಅಂದರೆ ಕರೆಂಟ್ ಕ್ಯಾರಿ ಚಾರ್ಜ್ಡ್ ಪಾರ್ಟಿಕಲ್ ಮೂವ್ ಆಗ್ತಾ ಇದೆ ಅಂದರೆ ದ ಡಿಸ್ಟೆನ್ಸ್ ಬಿಟ್ವೀನ್ ದ ಚಾರ್ಜ್ಡ್ ಪಾರ್ಟಿಕಲ್ ಇಸ್ ಗೋಸ್ ಆನ್ ಇನ್ಕ್ರೀಸಸ್, ಹೆಚ್ಚಿಗೆ ಆಗ್ತಾ ಹೋಗುತ್ತೆ. ಸೊ ಹಾಗಾಗಿ ಈ ಪಾಯಿಂಟ್ ಹತ್ರ ಈ ಚಾರ್ಜಿಂದು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡು ಕಂಟಿನ್ಯೂಯಸ್ಗೆ ಚೇಂಜ್ ಆಗುತ್ತೆ. ಚೇಂಜ್ ಆಗ್ತಾ ಇದೆ ಕಾರಣದಿಂದ ನಾವು ಚಾರ್ಜ್ದು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿಲ್ಲ. ಮತ್ತು ಕರೆಂಟ್ ಕ್ಯಾರಿಯಿಂಗ್ ಕಂಡಕ್ಟರ್ದು ಈ ಪರ್ಟಿಕ್ಯುಲರ್ ಪಾಯಿಂಟ್ ಹತ್ರ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಆಲ್ವೇಸ್ ಕಾನ್ಸ್ಟ್ಯಾಂಟ್ ಇರುತ್ತೆ. ಹೆಂಗೆ ಕಾನ್ಸ್ಟ್ಯಾಂಟ್ ಇರುತ್ತೆ ಅಂದರೆ, ಕರೆಂಟ್ ಈಸ್ ಫ್ಲೋಯಿಂಗ್ ಅಪ್ವರ್ಡ್, ಮೇಲೆ ಕರೆಂಟ್ ಹೋಗ್ತಾ ಇದೆ ಅಂದರೆ ಎಲೆಕ್ಟ್ರಾನ್ ಕೆಳಗಡೆಗೆ ಹೋಗ್ಬೇಕು. ಈ ಎಲೆಕ್ಟ್ರಾನ್ ಕೆಳಗಡೆಗೆ ಹೋಗ್ತಿದ್ದಾಗ ಇನ್ನೊಂದು ಎಲೆಕ್ಟ್ರಾನ್ ಬರುತ್ತೆ, ಇಲ್ಲಿಗೆ ಇನ್ನೊಂದು ಎಲೆಕ್ಟ್ರಾನ್ ಬರುತ್ತೆ, ಇನ್ನೊಂದು ಎಲೆಕ್ಟ್ರಾನ್ ಬರುತ್ತೆ. ಹಾಗಾಗಿ ಎಂಟೈರ್ ದಿಸ್ ಕಂಡಕ್ಟರ್ ನಮಗೆ ಚಾರ್ಜ್ ಫ್ಲೋ ಆಗ್ತಾನೆ ಇರುತ್ತೆ. ಹಾಗಾಗಿ ಈ ಪರ್ಟಿಕ್ಯುಲರ್ ಪಾಯಿಂಟ್ ಹತ್ರ ಇಲ್ಲಿರೋ ಎಲೆಕ್ಟ್ರಾನ್ ಫೀಲ್ಡ್, ಇಲ್ಲಿರೋ ಎಲೆಕ್ಟ್ರಾನ್ ಫೀಲ್ಡ್ ಎಲ್ಲ ಸಮ್ಮೇಷನ್ ಮಾಡ್ತೀವಿ, ಸಮ್ ಮಾಡ್ತೀವಿ. ಹಾಗಾಗಿ ಈ ಕಂಡಕ್ಟರಲ್ಲಿ ಕಂಟಿನ್ಯೂಸ್ಗೆ ಚಾರ್ಜ್ ಫ್ಲೋ ಆಗ್ತಾ ಇರೋದಕ್ಕೋಸ್ಕರ ಈ ಚಾರ್ಜ್ ಕೆಳಗಡೆಗೆ ಹೋದರೂ ಇನ್ನೊಂದು ಚಾರ್ಜ್ ಬಂದು ಆ ಜಾಗದಲ್ಲಿರುತ್ತೆ, ಇದಿಲ್ಲಿಗೆ ಹೋದರೂ ಇನ್ನೊಂದು ಚಾರ್ಜ್ ಬಂದಲ್ಲಿರುತ್ತೆ. ಹಾಗಾಗಿ ಚಾರ್ಜ್ ಈ ಕಂಡಕ್ಟರಲ್ಲಿ ಆಲ್ವೇಸ್ ಫ್ಲೋ ಆಗ್ತಾನೇ ಇರುತ್ತೆ. ಹಾಗಾಗಿ ಈ ಪರ್ಟಿಕ್ಯುಲರ್ ಪಾಯಿಂಟ್ ಹತ್ರ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಈಸ್ ಕಾನ್ಸ್ಟ್ಯಾಂಟ್. ಹಾಗಾಗಿ ನಾವು ಸ್ಟ್ರೈಟ್ ಕರೆಂಟ್ ಕ್ಯಾರಿಯಿಂಗ್ ಕಂಡಕ್ಟರ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡನ್ನ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತೀವಿ. ಆದರೆ ಇನ್ನೊಂದು ಇಂಪಾರ್ಟೆಂಟ್ ಪಾಯಿಂಟ್ ಸೀಮಾ, ಎ ಕರೆಂಟ್ ಕ್ಯಾರಿಯಿಂಗ್ ಕಂಡಕ್ಟರ್ ಪ್ರೊಡ್ಯೂಸಸ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಅರೌಂಡ್ ದಿಸ್ ಕಂಡಕ್ಟರ್. ಹಿಂಗೆ ಪ್ರೊಡ್ಯೂಸ್ ಮಾಡ್ತಾ ಇರುತ್ತೆ. ಈ ಕಡೆ ಸೈಡ್ ಇಂಟು ಇರುತ್ತೆ. ದಿಸ್ ಈಸ್ ಇಂಟು ದ ಬೋರ್ಡ್, ದಿಸ್ ಈಸ್ ಔಟ್ ಆಫ್ ದ ಪ್ಲೇನ್ ಆಫ್ ದ ಬೋರ್ಡ್, ಇದು ಔಟ್ ಬರುತ್ತೆ. ಓಕೆ, ಆದರೆ ಈ ಕರೆಂಟ್ ಕ್ಯಾರಿಯಿಂಗ್ ಕಂಡಕ್ಟರ್ ಪ್ರೊಡ್ಯೂಸ್ ಮಾಡ್ತಾ ಇರೋ ಫೀಲ್ಡ್ ಎಲ್ಲ ದೊಡ್ಡ ಜಾಗದಲ್ಲಿದೆ, ಹ್ಯೂಜ್ ಸ್ಪೇಸಲ್ಲಿದೆ. ಹಾಗಾಗಿ ನನಗೆ ಈ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ನ ಯೂಸ್ ಮಾಡಿಕೊಂಡೋಕ್ಕೆ ಬರಲ್ಲ, ಯೂಸ್ ಮಾಡ್ಕೊಂಡೋಕ್ಕಾಗಲ್ಲ. ಹಿಯರ್ ಆ್ಯಕ್ಚುಲಿ ದ ಕರೆಂಟ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ produced by this current carrying conductor is occupied in a huge space. ಇಲ್ಲಿ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಇದೆ, ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಇದೆ ಅಂದರೆ ಎನರ್ಜಿ ಇರುತ್ತೆ. ಆ ಎನರ್ಜಿನ ನಾವು ಯುಟಿಲೈಸ್ ಮಾಡ್ಕೋಬೇಕು ಅಂದರೆ ಸ್ವಲ್ಪ ತೊಂದರೆ ಆಗುತ್ತೆ ಇಲ್ಲಿ. ಸಿ, ಫಾರ್ ಎಕ್ಸಾಂಪಲ್, ನನಗೆ ಕಾಫಿ ಒಂದು ಮನೆಗೆ ಹೋಗಿದ್ದೀನಿ ಗೆಸ್ಟಾಗಿ, ಹಾಗಾಗಿ ಅವರು ಕಾಫಿ ಕೊಟ್ಟರು. ಕಾಫಿ ಒಂದು ಸಣ್ಣ ಕಪ್ಪಲ್ಲಿ ಹಾಕಿ ಕೊಟ್ರು ಅನ್ಕಲ್ರಿ, ಕಾಫಿ ಕಮ್ಮಿ ಜಾಗದಲ್ಲಿರುತ್ತೆ, ನಾನು ಆರಾಮ್ಸೆ ಕುಡಿಬೋದು. ಇದೇ ಒಂದು ಸಣ್ಣ ಕಪ್ ಕಾಫಿನಿ ಒಂದು ದೊಡ್ಡ ಡ್ರಮ್ಗೆ ಹಾಕ್ಕೊಟ್ರೆ ಅನ್ಕಲ್ರಿ, ಅದು ಎಲ್ಲೋ ಒಳಗೆ ಎಲ್ಲೋ ಕೆಳಗಡೆ ಇರುತ್ತೆ, ಕುಡಿಯೋಕ್ಕೆ ಬರಲ್ಲ. ನಾವು ಸ್ಟ್ರಾ ಹಾಕಿ ಕುಡಿಬೇಕಂದ್ರೇನು ಸಕ್ ಮಾಡ್ತೆ ಗಾಳಿ ಬರುತ್ತೆ ಬಿಟ್ಟರೆ ಟೀ ಬರಲ್ಲ. ನೀವು ಜ್ಯೂಸ್ ಹಾಕ್ತೆ ಜ್ಯೂಸ್ ಬರಲ್ಲ. ಅಂದರೆ ನಾವು ತಗೊಂಡೇ ಐಟಮ್ ಕಮ್ಮಿ ಜಾಗದಲ್ಲಿರುತ್ತೆ, ಕಮ್ಮಿ ಜಾಗದಲ್ಲಿ ಆಕ್ಯುಪೈ ಮಾಡ್ತೆ, ಅದನ್ನು ನಾನು ಯುಟಿಲೈಸೇಷನ್ ಈಸಿ ಆಗುತ್ತೆ, ಈಸಿಗೆ ತಗೋಬೋದು. ಇಲ್ಲಿ ಈ ಕರೆಂಟ್ ಕ್ಯಾರಿಯಿಂಗ್ ಕಂಡಕ್ಟರ್ ಪ್ರೊಡ್ಯೂಸ್ ಮಾಡ್ತಾ ಇರೋದು ಜ್ಯೂಸ್ನ ದೊಡ್ಡ ಡ್ರಮ್ಗೆ ಹಾಕಿ ಕೊಟ್ಟಿದ್ದಾಗ ಇಲ್ಲಿರೇ ಎನರ್ಜಿ, ಇಲ್ಲಿರೇ ಫೀಲ್ಡ್ ಎಲ್ಲ ಏರಿಯಾದಲ್ಲಿದೆ. ಹಾಗಾಗಿ ಯುಟಿಲೈಸೇಷನ್ ನಾನು ಯೂಸ್ ಮಾಡ್ಕೋಬೇಕಿದು ಅಂದರೆ ಆಗಲ್ಲ. ಓಕೆನಾ? ಸೊ ದಟ್ಸ್ ವೈ now what we are going to do, this current carrying conductor we will bend in the form of a circular ring. We will bend in the form of a circular ring. This is a circular ring. ಈ ಸರ್ಕ್ಯುಲರ್ ರಿಂಗ್ ಅಲ್ಲಿ ಕರೆಂಟ್ ಅನ್ನು ನಾವು ಕಲಿಸಿದೀವಿ ಅಂದ್ರೆ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಇಲ್ಲಿ ಹಿಂಗಿರುತ್ತೆ, ಈ ತರ ಇರುತ್ತೆ. ಈ ಎಲಿಮೆಂಟಲ್ ಪೋರ್ಷನ್ ಹಿಂಗಿರುತ್ತೆ, ಈ ಥರ. ಅದೇ ಥರ ಎಲ್ಲ ಎಲಿಮೆಂಟಲ್ ಪೋರ್ಷನ್ ಫೀಲ್ಡ್ ಇರುತ್ತೆ, ಎಲ್ಲ ಕಡೆ ಇರ್ತದೆ. ಬಟ್ ನಾನು ಒಂದು ಕರೆಂಟ್ ಕ್ಯಾರಿಯಿಂಗ್ ಸ್ಟ್ರೈಟ್ ಕಂಡಕ್ಟರು 1,00,000 ಫೀಲ್ಡ್ ಲೈನ್ಸ್ನ ಪ್ರೊಡ್ಯೂಸ್ ಮಾಡಿದೆ ಅಂದರೆ ಈ 1,00,000 ಎಂಟೈರ್ ಸ್ಪೇಸಲ್ಲಿ ಇರ್ತಾವೋ. ಆದರೆ ಇದೇ ಸ್ಟ್ರೈಟ್ ಕಂಡಕ್ಟರ್ನ ನಾನು ಸರ್ಕ್ಯುಲರ್ ಪಾತಲ್ಲಿ ಬೆಂಡ್ ಮಾಡಿದ ಮೇಲೆ ಇದು 1,00,000 ಫೀಲ್ಡ್ ಲೈನ್ಸ್ನೇ ಪ್ರೊಡ್ಯೂಸ್ ಮಾಡ್ತದೋ. ಆಲ್ 1,00,000 ಫೀಲ್ಡ್ ಲೈನ್ಸ್ ಆರ್ ಪಾಸಿಂಗ್ ಇನ್ ದಿಸ್ ಸ್ಮಾಲ್ ಏರಿಯಾ. ಈ ಕಡೆ ಸೈಡ್ ಇನ್ಫಿನಿಟಿವರೆಗೆ ಹೋಗ್ಬೋದು, ಆದರೆ ಒಳಗೆ ಬರ್ತಾ ಇರೋ ಫೀಲ್ಡ್ ಲೈನ್ ಪೂರ್ತಿ ಇದೇ ಏರಿಯಾದಲ್ಲಿ ನಿಮಗೆ 1,00,000 ಫೀಲ್ಡ್ ಲೈನ್ಸ್ ಇರುತ್ತೆ. ಅಂದರೆ ವಿತಿನ್ ದ ಸರ್ಕ್ಯುಲರ್ ಲೂಪ್ ಫೀಲ್ಡ್ ಈಸ್ ಸೋ ಸ್ಟ್ರಾಂಗ್, ವೆರಿ ಸ್ಟ್ರಾಂಗ್ ಇರುತ್ತೆ. ಎಲ್ಲ ಫೀಲ್ಡ್ ಲೈನ್ಸ್ ಈ ಕಮ್ಮಿ ಜಾಗದಲ್ಲಿ ಪಾಸ್ ಆಗಬೇಕು. ಸೊ ಹಾಗಾಗಿ ಎ ಕರೆಂಟ್ ಕ್ಯಾರಿಯಿಂಗ್ ಕಂಡಕ್ಟರ್ ಇಸ್ ಎ ಸ್ಟ್ರೈಟ್ ಕಂಡಕ್ಟರ್ ಅಂದರೆ ಫೀಲ್ಡ್ ಈಸ್ spread in entire area. But if it is bent in the form of a circular circle, then the entire magnetic field is exist here inside the coil. Field is so strong, outside field decreases. Okay, this is how the magnetic field produced by a circular ring. I would like to study magnetic field at any point along the axis of a current carrying circular loop. ಬರೇ ಆಕ್ಸೆಸ್ ಮೇಲೇ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತಿದ್ದೀವಿ. ಆಕ್ಸೆಸ್ ಬಿಟ್ಟು ಬೇರೆ ಜಾಗದಲ್ಲಿ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡೋಕ್ಕೆ ಬರಲ್ಲನ ಅಂದರೆ ಬರುತ್ತೆ, ಆದರೆ ಅದು ಸ್ವಲ್ಪ ಡಿಫಿಕಲ್ಟ್ ಆಗುತ್ತೆ. ಈಗ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಅಟ್ ಎನಿ ಪಾಯಿಂಟ್ ಡ್ಯೂ ಟು ಕರೆಂಟ್ ಕ್ಯಾರಿಯಿಂಗ್ ಸರ್ಕ್ಯುಲರ್ ಲೂಪ್ ಅಲಾಂಗ್ ದ ಆಕ್ಸೆಸ್ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತೀವಿ. ದಿಸ್ ಈಸ್ ವೆರಿ ವೆರಿ ಇಂಪಾರ್ಟೆಂಟ್ ಫಾರ್ ಬೋರ್ಡ್ ಎಕ್ಸಾಮಿನೇಷನ್. You will get every year for annual examination for 5 marks. Understand this concept very carefully. When we have a circle like this, then axis will be come out of the plane of the board. ನಾವು ಇಲ್ಲಿ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಬೇಕು ಅಂದರೆ ಅದು ಬೋರ್ಡ್ ಮೇಲೆ ತೋರಿಸೋಕ್ಕೆ ಬರಲ್ಲ. ಹಾಗಾಗಿ ಸರ್ಕ್ಯುಲರ್ ಕಾಯಿಲ್ನ ನಾವು ಈ ಥರ ತೋರಿಸಲ್ಲ. ವಿ ವಿಲ್ ರಿಪ್ರೆಸೆಂಟ್ ಸರ್ಕ್ಯುಲರ್ ಕಾಯಿಲ್ ಲೈಕ್ ದಿಸ್. We will represent like this. This is the center of the circular loop. The line passing through the center of the the line passing through center of the circle and perpendicular to circular section is called axis. Axis of the loop. This is axis. This is axis of the loop. So if we take any point on the axis, it is equidistant from every point on the circular loop. So axis is a symmetry. Axis ಅನ್ನೋದು symmetry ಆಗಿರುತ್ತೆ. So this is circular coil. Here we will see this is a bangle, circular coil. This is the axis of the circular coil. Any point on the axis is equidistant from every element on this circular section. So that's why axis is a symmetry for a given circular loop. See here, now we have placed a circular coil like this. We have placed it like this. Okay, na? Then the axis comes in this side. Okay, and one very important, see, whenever a circular loop is shown like this, when I move from left to right, whichever the section will come, that is outside of the plane of the paper. This is inside. See, this one is this. This is outside. This is outside one. This is inside one. This is important logic. Always this is outer side. This will be inner side. You remember this, important. Now, this is the center of the circular loop. Now, this will be the radius of the loop. Radius of the loop, I will take it as capital R. Radius of the loop is capital R. Now, I want to calculate magnetic field here. As of now, we know only Biot and Savart law. There is no other law. We know. So only by applying Biot and Savart law only we should solve this question. So for that, for Biot and Savart law, if we have a conductor like this, if it carries current, then we'll select a point, we'll select a elemental portion, we'll join these two, distance is r, the angle between elemental portion and position vector is theta. Then dB is equal to mu naught by 4 pi I dl sin theta divided by r square. This is what the conclusion of Biot and Savart law. So this I am going to apply here. So here what I am doing, I will select one small elemental portion say dl. See here another important point I will tell you. So if it is carrying current in this direction, current is going here into, here it is coming out. So that means current is flowing like this. At the top, it is coming out towards you. Current is going like this here, here it is going into. So for this elemental portion, current is going into. For this elemental portion, current is coming out. So this is very, very, very important. See here, current is coming towards you. Current is going like this. Current is coming out here, current is going here into. Coming out into, like this. So here current is in this direction. For this elemental portion, current is in this direction means curling fingers indicates the direction of magnetic field. So current coming out, magnetic field will be in this direction. Here current is going into, magnetic field will be in this direction. That means we have to understand very important point. Along the axis, magnetic field is in this direction. Even this side as well as even this side. Magnetic field will be in this direction. Here also magnetic field will be in this direction. See, right side of the coil, left side of the coil. Both the sides, magnetic field direction is along the positive x-axis. This is very, very important point for competitive. Now see, this is an elemental portion. We need to join this point with this elemental portion. This is called actually R. This is called actually R. This is R. Okay. This portion from center to this point is at a distance x. The value of this R can be written as root over. Why? Because it forms a right angled triangle, Pythagorean theorem. Capital R square plus x square is the distance. Okay. Now here understand very carefully this one. Here magnetic current is coming out of the plane of the board. So magnetic field line is going like this. Magnetic field line will be like this. Magnetic field will be like this. So at this particular point, maybe the magnetic field line which is coming is going like this. So that's why for this circular loop, here you will have one magnetic field line. For that magnetic field line, I am going to draw a tangent. That tangent I will get this side. This you have to realize very carefully. here current is coming this side, magnetic field line is going like this. Here tangent will be like this, it is going like this, so tangent will be like this. This may take long path and it will come back again because it is a circular loop. So in this way, here may be a line passing like this. So for that line I have drawn a tangent. So this is the direction of magnetic field due to small elemental portion. Small portion of conductor produces small magnetic field that I have represented here. ನಾವು ಇಲ್ಲಿ ಕರೆಂಟ್ ಈ ಕಡೆ ಸೈಡ್ ಇದರಿಂದ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಲೈನ್ ಹಿಂಗಿರುತ್ತೆ, ಈ ಥರ ಬರುತ್ತೆ, ಈ ಥರ ಬರುತ್ತೆ, ಈ ಥರ ಬರುತ್ತೆ. ಈ ಪರ್ಟಿಕ್ಯುಲರ್ ಪಾಯಿಂಟ್ ಹತ್ರ ಕರ್ವುಡ್ ಲೈನ್ಗೆ ಟ್ಯಾಂಜೆಂಟ್ ಡ್ರಾ ಮಾಡುತ್ತೆ, ಫೀಲ್ಡ್ ಹಿಂಗೆ ಬಂತು. ಅದೇ ಥರ ಆಪೋಸಿಟ್ ಎಲಿಮೆಂಟ್ದೊಂದು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತಾ ಇದ್ದೀನಿ ನಾನು. ಇಲ್ಲಿ ಕರೆಂಟ್ ಒಳಗೆ ಹೋಗ್ತಾ ಇದೆ, ಹಾಗಾಗಿ ಫೀಲ್ಡ್ ಹಿಂಗೆ ಬರುತ್ತೆ, ಈ ಕಡೆ ಸೈಡ್ ಹಿಂಗೆ ಬರುತ್ತೆ, ಹಿಂಗೆ ಬರುತ್ತೆ, ಹಿಂಗೆ ಬರುತ್ತೆ. ಹಾಗಾಗಿ ಈ ಪರ್ಟಿಕ್ಯುಲರ್ ಪಾಯಿಂಟ್ ಹತ್ರ ಹಿಂಗೋಗೆ ಫೀಲ್ಡ್ ಲೈನ್ಗೆ ನಾನು ಟ್ಯಾಂಜೆಂಟ್ ಡ್ರಾ ಮಾಡಬೇಕು. ಟ್ಯಾಂಜೆಂಟ್ ಡ್ರಾ ಮಾಡುತ್ತೆ, ಡಿ ಬಿ ಹಿಂಗೆ ಬರುತ್ತೆ. ಏನು ಓಕೆನಾ? ದಿಸ್ ಇಸ್ ಕ್ಲಿಯರ್ ನೋ? ಸೊ ದಟ್ ಮೀನ್ಸ್ ಈ ಎಲಿಮೆಂಟ್ ಇಂದ ಈ ಕಡೆ ಸೈಡ್ ಇದೆ, ಈ ಎಲಿಮೆಂಟ್ ಇಂದ ಈ ಕಡೆ ಸೈಡ್ ಇದೆ ನೋಡಿ. ಈ ಪರ್ಟಿಕ್ಯುಲರ್ ಪಾಯಿಂಟ್ದು ಈ ಕಡೆ ಸೈಡ್ ಇದೆ, ಈ ಪರ್ಟಿಕ್ಯುಲರ್ ಪಾಯಿಂಟ್ದು ಈ ಕಡೆ ಸೈಡ್ ಇದೆ. ಈಗ ಇದು ತಗೊಳ್ತೆ ಹಿಂಗಿರುತ್ತೆ, ಇದು ತಗೊಳ್ತೆ ಹಿಂಗಿರುತ್ತೆ. ಹಾಗಾಗಿ ಇಲ್ಲಿ ನಾನು ಈ ಫೀಲ್ಡ್ ಲೈನ್ ಈ ಎಲಿಮೆಂಟ್ದು ಇನ್ನೊಂದು ಎಲಿಮೆಂಟ್ ತಗೊಳ್ತೆ ಹಿಂಗೆ ಬರುತ್ತೆ, ಹಿಂಗೆ ಬರುತ್ತೆ, ಹಿಂಗೆ ಬರುತ್ತೆ, ಹಿಂಗೆ ಬರುತ್ತೆ, ಹಿಂಗೆ ಬರುತ್ತೆ, ಹಂಗೊಳಗೆ ಹೋಗುತ್ತೆ. ಹಾಗಾಗಿ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಹಿಂಗಿರುತ್ತೆ. ಅಂದರೆ ನಾನು ಅಲ್ಲಿ ಕಾಕ್ ಆಟ ಆಡ್ತೀವಲ್ಲ, ಆ ಕಾಕ್ನ ಇಮ್ಯಾಜಿನ್ ಮಾಡುತ್ತೆ. ಒಂದೊಂದು ಫೆದರ್ ಒಂದೊಂದು ಡೈರೆಕ್ಷನ್ನ ರಿಪ್ರೆಸೆಂಟ್ ಮಾಡುತ್ತೆ. ಅಂದರೆ ಇಲ್ಲಿ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಡ್ಯೂ ಟು ದಿಸ್ ಎಂಟೈರ್ ಕಂಡಕ್ಟರ್ ವಿಲ್ ಬಿ ಲೈಕ್ ಎ ಫೆದರ್ ಕಾಕ್. ಅಂದರೆ ನಿಮಗೆ ಅಪ್ರಾಕ್ಸಿಮೇಟ್ಗೆ ಹೆಂಗಿರುತ್ತೆ ಅಂದರೆ, ಇಲ್ಲಿ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಹಿಂಗಿರುತ್ತೆ, ಈ ಥರ ಇರುತ್ತೆ. ಇಲ್ಲಿ ಇದ್ರದ್ದು ಈ ಟ್ಯಾಂಜೆಂಟ್, ಇದ್ರದ್ದು ಈ ಟ್ಯಾಂಜೆಂಟ್, ಇದ್ರದ್ದು ಹಿಂಗೆ ಟ್ಯಾಂಜೆಂಟ್, ಹಿಂಗೆ ಟ್ಯಾಂಜೆಂಟ್, ಹಿಂಗೆ ಟ್ಯಾಂಜೆಂಟ್, ಈ ಥರ ಇರುತ್ತೆ ಇಲ್ಲಿ ಫೀಲ್ಡ್. ಈ ಪರ್ಟಿಕ್ಯುಲರ್ ಜಾಗದಲ್ಲಿ ಹಿಂಗೆ 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 ಕರ್ವ್ ಇರುತ್ತೆ, ಈ ಥರ ಇರುತ್ತೆ, ಈ ಥರ ಇರುತ್ತೆ. ಇದು ಮೇಲಿಂದು, ಇದು ಕೆಳಗಿಂದು, ಇದು ಮಧ್ಯದಿಂದು, ಇದು ಕಡೆ ಸೈಡ್ ಮಧ್ಯದಿಂದು, ಈ ಥರ ಇರುತ್ತೆ ಫೀಲ್ಡ್ ಇಲ್ಲಿ. ಓಕೆನಾ? ಸೊ ನೌ ವಾಟ್ ಐ ಆಮ್ ಡೂಯಿಂಗ್, ಐ ಆಮ್ ರಿಸಾಲ್ವಿಂಗ್ these components. One is a horizontal component, another one is a vertical component. For this vertical component, this is horizontal component. We need to name the components. Okay, for that what I am doing, if we take here say theta, for example, if this is theta, this is 90 minus theta, this is 90 minus theta. Okay, this and this perpendicular, this will become theta. Okay, then this will become 90 minus theta, this will become theta. Okay, this is one aspect, you can take like this. Okay, then you will get this as this, you will get it as dB cos theta. Okay, this you will get it as dB sin theta. Okay, this again theta, so that's why this is again dB cos theta, this is dB sin theta. Okay, see here, if I take angle theta here, I am getting cos. If I take angle theta here, this you will get cos, this you will get sin. ಇಲ್ಲಿ ಸೈನ್ ಬರ್ತಾ ಇದೆಯಾ, ಕಾಸ್ ಬರ್ತಾ ಇದೆಯಾ ಅನ್ನೋದ ಮೇಲೆ ಏನು ಡಿಪೆಂಡ್ ಆಗಲ್ಲ. ನಾನು ಆ್ಯಂಗಲ್ ಹೆಂಗೆ ತಗೊಳ್ತೀನೋ ಅದ್ರ ಪ್ರಕಾರ ಇಲ್ಲಿ ಕಾಂಪೊನೆಂಟ್ ಬರುತ್ತೆ. ಸೈನ್ ಇರಲಿ, ಕಾಸ್ ಇರಲಿ, ಡೋಂಟ್ ವರಿ. ಜಾಮೆಟ್ರಿ ಆಟೋಮೆಟಿಕ್ಗೆ ಚೇಂಜ್ ಆಗುತ್ತೆ, ಆಟೋಮೆಟಿಕ್ಗೆ ನಿಮಗೆ ಕರೆಕ್ಟ್ ಆನ್ಸರ್ ಬರುತ್ತೆ. ನಾವು ಆ್ಯಂಗಲ್ ಇಲ್ಲಿ ತಗೊಳ್ತಾ ಇದೀವ್ಯಾ, ಇಲ್ಲಿ ತಗೊಳ್ತಾ ಇದೀವ್ಯಾ ಅನ್ನೋದ ಮೇಲೆ ಇಲ್ಲಿ ಡಿ ಬಿ ಕಾಸ್ ಟೀಟಾನ ಅಥವಾ ಡಿ ಬಿ ಸೈನ್ ಟೀಟಾನ ಅನ್ನೋದು ಬರುತ್ತೆ. Here in this case vertical components are cancels each other, vertical components cancel ಆಗುತ್ತೆ. horizontal components added up, horizontal components add ಆಗ್ತಾವೆ. ಇಲ್ಲಿ ಎರಡೇ ಇರುತ್ತೆ, ನಾನು 2 dB cos theta ತಗೊಳ್ತೀನಿ. ಬಟ್ ಇಲ್ಲಿ ಎರಡಿಲ್ಲ, ಬಾಲ ಇದಾವೆ ಇಂಥವು. ಆಲ್ರೆಡಿ ತೋರಿಸಿದೀವಲ್ಲ ಡಯಾಗ್ರಾಮ್, ಬಾಲ ಇರ್ತಾವ, ಇನ್ಫಿನಿಟಿ ಇರ್ತಾವ. ಹಾಗಾಗಿ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಅಟ್ ದಿಸ್ ಪರ್ಟಿಕ್ಯುಲರ್ ಪಾಯಿಂಟ್ ಬಿ, ಟೋಟಲ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಬಿ ಕ್ಯಾನ್ ಬಿ ಅನ್ ಇಂಟಿಗ್ರಲ್ ಆಫ್ dB cos theta. ನಾನು ಈ dB cos theta ನ ಇಂಟಿಗ್ರೇಟ್ ಮಾಡಬೇಕು. ಈ ಪಾಯಿಂಟ್ ಹತ್ರ ಸ್ಟಾರ್ಟ್ ಮಾಡಿ ಇದು ಎಲ್ಲ ಇಂಟಿಗ್ರೇಟ್ ಮಾಡ್ತಾ ಬರಬೇಕು. ಅಂದರೆ 0 to L ಇಂಟಿಗ್ರೇಟ್ ಮಾಡಬೇಕು. ದಿಸ್ ಇಂಟಿಗ್ರೇಷನ್ ವಿ ಶುಡ್ ಡು. ನಾನು ಅಗೈನ್ ಹೇಳ್ತಾ ಇದ್ದೀನಿ, ಇಲ್ಲಿ ಕಾಸ್ ಇದೆಯಾ ಸೈನ್ ಇದೆಯಾ ಅನ್ನೋದೇನು ಸಂಬಂಧ ಇಲ್ಲ. ನಾವು ಆ್ಯಂಗಲ್ ಹೆಂಗೆ ತಗೊಳ್ತೀವಿ ಅನ್ನೋದ ಮೇಲೆ ಅದು ಅಲ್ಲಿ ಕಾಸು ಸೈನ್ ಬರುತ್ತೆ ಅಷ್ಟೇ. ಡೋಂಟ್ ವರಿ, ಓಕೆನಾ? ಸೊ ಟೋಟಲ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಅಟ್ ದಿಸ್ ಪಾಯಿಂಟ್ is the integration of this component dB cos theta. Vertical components cancel, there is no magnetic field this side. So hagagi at any point on the axis magnetic field will be like this. Here strength is more, goes on, strength decreases. That is the difference. Even this side also magnetic field is in one direction only, always along the positive x-axis. ಈ current direction reverse ಮಾಡ್ತೆ, field reverse ಆಗುತ್ತೆ. ಇಲ್ಲಿ ಹೊರಗೆ ಬರ್ತಾ ಇರೋದಕ್ಕೋಸ್ಕರ ಫೀಲ್ಡ್ ಈ ಕಡೆ ಸೈಡ್ ಇದೆ. ಅದೇ ಇಲ್ಲಿ ಒಳಗೆ ಹೋಗ್ತೆ ಫೀಲ್ಡ್ ಹಿಂಗಿರುತ್ತೆ, ಈ ಕಡೆ ಸೈಡ್ ಇರುತ್ತೆ. ಇಲ್ಲಿ ಇಂಟು ಇರುತ್ತೆ, ಈ ಕಡೆ ಸೈಡ್. ಇಲ್ಲಿ ಆಟೋಮೆಟಿಕ್ಕಾಗಿ ಇಲ್ಲಿ ಇಂಟು ಇದೆ ಅಂದರೆ ಇಲ್ಲಿ ಔಟ್ ಇರುತ್ತೆ, ಇದು ಈ ಕಡೆ ಸೈಡ್ ಇರ್ತದೆ. ಅಷ್ಟೇ, ಸಿಂಪಲ್. ಲೆಫ್ಟ್ ಸೈಡ್, ರೈಟ್ ಸೈಡ್, ಎವ್ರಿವೇರ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಡೈರೆಕ್ಷನ್ ಇಸ್ ರಿಮೈನ್ಸ್ ಸೇಮ್. ದ ಡೈರೆಕ್ಷನ್ ಆಫ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಕ್ಯಾನ್ ಬಿ ನೋನ್ ಬೈ ಯೂಸಿಂಗ್ ಸಿಂಪಲ್ ರೈಟ್ ಹ್ಯಾಂಡ್ ಥಂಬ್ ರೂಲ್. ಈಸಿಗೆ ಆರಾಮ್ಸೆ ನಾನು ಇದು ಔಟ್ ಸೈಡ್, ಫೀಲ್ಡ್ ಈ ಕಡೆ ಸೈಡ್ ಇರುತ್ತೆ. ಇದು ಇಂಟು ಹಿಂಗೆ ಬಂದ್ಬಿಟ್ಟು ಫೀಲ್ಡ್ ಈ ಕಡೆ ಸೈಡೇ ಇರುತ್ತೆ. ಅಷ್ಟು ಈಸಿ. ಇದನ್ನು ನಾನು ಇಂಟಿಗ್ರೇಟ್ ಮಾಡ್ತೀನಿ. ಬಯೋಟ್ ಆ್ಯಂಡ್ ಸಾವರ್ಟ್ ಲಾ ಇಂದ ಡಿ ಬಿ ವ್ಯಾಲ್ಯೂ ತೊಗೊಂಬರ್ತೀವಿ. ಸೊ ನಾವು ಬಿ ಈಸ್ ಈಕ್ವಲ್ ಟು ಇಂಟಿಗ್ರಲ್ ಆಫ್ 0 to L. ಡಿ ಬಿ ವ್ಯಾಲ್ಯೂ ನೋಡಮ್ಮ, ಡಿ ಬಿ ವ್ಯಾಲ್ಯೂ ಕ್ಯಾನ್ ಬಿ ಕ್ಯಾಲ್ಕುಲೇಟೆಡ್ ಫ್ರಮ್ ಹಿಯರ್. ಡಿ ಬಿ ಈಸ್ simply we'll write like mu naught by 4 pi I by I. Elemental portion is dl. Here we have sin theta. Theta is the angle between I and dl. Here current is out of the plane of the board. dl is like this. That means this portion dl is in this direction, current also in this direction. idl will be in this direction. Ideal is in this direction, but R is this. That means, see here carefully, this is very important point. This is axis. I am joining R like this from the conductor. From the conductor we are drawing like this. So when a conductor and R are arranged like this, angle between R and DL is this 90 degrees. It will be 90 degrees. This you have to realize very carefully. When you imagine like this, angle between these two is 90 degrees. It is 90 degrees. This is important. Angle between DL and R is theta. Here it is inclined. Don't measure angle this. This is not the angle. Straight conductor will be like this. Example, DL is along this line. Along this line, piece of chalk is going like this. So angle between these two is 90 degrees. This is DL. This is line. Angle between them is 90 degrees. So that sin 90, this is sin 90 degree divided by this distance we should take here R. R value is R square plus x square root 2 whole square. Root 2 square cancel. Still we have cos theta here. So we will maintain cos theta as it is. So now magnetic field B is equal to mu naught by 4 pi I is constant. So mu naught by 4 pi I will write outside. Side 90 is 1. Okay. Otherwise we will write one more step. Later we'll take common. DL is as it is. This is 1 divided by R square plus x square. Afterwards we need to calculate cos theta. See, we have theta here. Okay, if theta is here, cos theta Cos theta is adjacent side by hypotenuse. Angle is here, so we have to calculate for this right angle triangle. This is theta, so adjacent side by hypotenuse. Adjacent side is r. Hypotenuse I'll write like this: r square plus x square whole power 1 by 2. Okay, here everything is constant except dl. So magnetic field B is equal to mu naught by 4 pi I. Bases are same, powers can be added, so this can be written as r square plus x square whole power 3 by 2. Here one r is there, that will write outside. Integral of dl from 0 to L. We know integral of dl is L. So magnetic field B is equal to mu naught by 4 pi I r divided by r square plus x square whole power 3 by 2. Integral of dl is L. Upper limit is L. Otherwise we'll write one more step what is there. For this, upper limit is L minus lower limit is 0. So you will get again L. So that's why I am writing it is L. The value of L is 2 pi r, 2 pi capital R. Why? Because L is circumference of the circular loop. Circumference of the circular loop, circumference is 2 pi r. Here capital R is the radius of the circular loop. So that's why magnetic field B is equal to mu naught by 4 pi I capital R. This is 2 pi capital R divided by r square plus x square whole power 3 by 2. So finally we will write this equation like this in this box. See, this is the final result. Magnetic field is B, mu naught by 4 pi I'll maintain as it is. Okay na, 2 pi I'll write here I capital R square. R into R is R square divided by R square plus X square whole power 3 by 2. This is how we are going to write. This 2 pi you can cancel with this, you will get mu naught by 2. Okay na? This is the magnetic field at any point along the axis of a current carrying circular loop. Just now we have derived magnetic field at any point along the axis. B is equal to mu naught by 4 pi. Here we got 2 pi. This 2 pi I can write it as angle of the circular loop, that can be written as theta. Okay, we have I r square divided by r square plus x square whole power 3 by 2. This is for only one turn of the loop. If we have 2 turns, 3 turns, 4 turns, then that n I'll write here. So that means this expression is going to be very useful in solving competitive exams. Magnetic field at any point due to current carrying circular loop at any point along the axis is B is equal to mu naught by 4 pi theta n I r square by r square plus x square whole power 3 by 2. How this is going to be helpful for us, we'll see now. See carefully. At any point I have calculated. Now I will calculate at the center. At the center of the coil. Center of the coil. Center of the coil means here. So when point is here, distance is x. When it comes here, x decreases. When it comes here, x further decreases. When it comes here, x is 0. At the center means x is equal to 0. When we substitute here x is equal to 0, the magnetic field B is mu naught by 4 pi theta n I r square whole divided by x is 0, r square whole power 3 by 2, 2 to cancel, so you will get r cube. This r square cancels cube. So magnetic field at the center B is equal to mu naught by 4 pi theta ni by r. See here, for one turn n value is 1. Okay na? Theta value becomes 2 pi. So this is for n turns. this expression for n turns. For example, for one turn, only for one turn, then this B can be written as mu naught by 4 pi. Theta value for one turn is 2 pi. 2 turns it is 4 pi. 3 turns it is 6 pi. I by R. Pi pi cancel, it cancels 2 times. So magnetic field is simply mu naught I by 2R. Okay, this is for one turn. This is for n turns. Okay, that means, see here, compare these two. Denominator is decreased like anything. So that's why magnetic field is maximum at the center. Magnetic field is maximum at the center. As you move this side, field decreases. As you move this side, field also decreases. And one more important thing for competitive examination is that magnetic field is maximum. Field is maximum. See here, in this case, current is coming like this, field is in this direction, field is positive. So field is positive. Any vector in the direction of positive x-axis can be taken as positive field. So positive field is represented in positive quadrants. So field is maximum at the center. So from here onwards, field decreases like this. This side field decreases like this. So this is the variation of magnetic field along the axis of a current carrying circular loop. For example, current direction is reversed. Here it is going into, field is in this direction. Here it is into, then it is out. If it is out, field is in this direction. Field is along the negative x-axis. Field is along the negative x-axis. That's why if the current direction is reversed, then the graph, variation of magnetic field, can be represented like this. This is how a variation of magnetic field can be represented. Magnetic field will be maximum at the center. This side decreases. This side also decreases. This is how we are going to represent variation of magnetic field. So magnetic field at any point along the axis of a current carrying circular loop, B is equal to mu naught by 4 pi theta Ni R square by R square plus X square whole power 3 by 2. In board examination, if we can derive this, it will be enough. Anyway 2 pi will get here, 4 pi cancel marte hing barutte ashte. Idadru okay. But this form is more useful in competitive problems. At the center, this is very important. For n turns, this is for only one turn. See, if I take point here for example, see this point is close to this element. This point is far away from this element. There is no symmetry. So calculating magnetic field here is not impossible, but it is difficult. Okay, so that's why for PUC level, we will confine magnetic field due to current carrying circular loop only along the axis we will calculate. Axis ki maatrane magnetic field na calculate martivi. Innondu advantage ಏನಂದ್ರೆ ಈ ವೈರ್ ಏನು ಎಷ್ಟು ನಂಬರ್ ಆಫ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಲೈನ್ಸ್ ನ ಪ್ರೊಡ್ಯೂಸ್ ಮಾಡ್ತದೋ ಆ ಎಲ್ಲ ಲೈನ್ಸ್ ಈ ಸ್ಮಾಲ್ ರೀಜಿಯನ್ ಇಂದನೇ ಹೋಗ್ತವು. ಹಾಗಾಗಿ inside the circular coil, magnetic field density is more is concentrated here. Strong field will exist inside, outside field is weak. So now we will see some applications on straight conductors as well as circular conductors. See, for straight conductor, magnetic field B is equal to mu naught by 4 pi I by R into sin alpha plus sin beta for finite length. For infinite length long conductors, mu naught by 4 pi 2I by R. For semi-infinite conductors or semi-long conductors, mu naught by 4 pi I by R. These things are very important for current carrying conductors, straight conductors. For circular sections, magnetic field at any point along the axis is mu naught by 4 pi theta ni r square by r square plus x square whole power 3 by 2. Magnetic field at the center for n turns is mu naught by 4 pi theta ni by r. For only one turn, mu naught by 4 pi, mu naught I by 2r. These formulas you remember carefully. We will use these things only to solve the coming problems. If we have a conductor like this, it carries current in this direction, then we need to calculate magnetic field at point O. This is a long conductor, obviously. See how to calculate these kind of problems, magnetic field at this point. See, it is very easy. First look at the diagram carefully. In that, how many straight conductors are there? How many curves are there? Just count. Here 1, this is semicircular section, this is straight. Total 3 elements we have. First element here produces field into the board. Second one also produces into the board. Third one also produces into the board. So we need to find 3 magnetic fields. So finally the magnetic field is into, for first conductor, see this is semi-infinite length conductor. So answer is mu naught by 4 pi I by, this is the radius of the circular loop, then it is r. For this section plus, this is also into the board, but it is not even have full circle. So that's why the formula for this magnetic field B is equal to mu naught by 4 pi theta ni by r is going to help us, because here mu naught by 4 pi theta value is only pi, not even 2 pi, it is less than 2 pi. We don't have even one turn, so n is 1, I by r, so pi cancel. So then you will get magnetic field is mu naught I by 4r. This is important, so that's why this expression is going to help a lot. Okay, so that's why magnetic field due to this is mu naught by 4 pi theta, we have written here pi, n is 1 turn, I is I, r. After simplification we got this mu naught I by 4r plus again this is another semi-finite, so mu naught by 4 pi I by r is the answer. These two we can add, you will get this is 2i. So no need to write this. So you take the common parameters outside. Mu naught is common, I is common, 4 is common. This is also smaller is common. Then it is 2 by pi plus 1. So this is the answer. In that way we are going to calculate. Next application. Next problem is like this. This is a long conductor, but here we have a one semicircular section followed by another long conductor like this. See, if it carries current I, it also carries current I, the same current is passing. Now they'll ask you to calculate magnetic field at point O, which is the center of the semicircular arc. Here also one straight conductor, one curve, one arc, one straight conductor, total 3 elements. But this point is along the axis of a conductor. Along the axis of a current carrying conductor, magnetic field is 0. So B is equal to, due to this conductor is 0, due to this conductor is also 0, but due to this conductor, mu naught by 4 pi, theta is pi, I by the radius is given as r, then r. So this is cancelled. So magnetic field you will get mu naught I by 4r. Okay. The next application. So next problem will be like this. For example, this is one semicircular arc, and this is a straight conductor, and this is another semicircular arc like this. At point O they have asked, this radius is say r, this radius is say maybe 3r for example. So current is going in anti-clockwise direction. Then they'll ask you to calculate magnetic field here. Magnetic field B is equal to, here I have one straight finite length conductor, arc, conductor, finite length straight conductor, arc, total 4 elements. Due to this element, this point is along the axis of a conductor, so answer is 0. Due to this, we are doing many times, we got mu naught I by 4r, this I have substituted straight away, plus this conductor is 0. For this conductor, except radius is different, that's it, remaining all same. Except radius, remaining all same. For this I'll calculate here B is equal to mu naught by 4 pi. It is also semicircle, angle is pi, I by radius is 3r. So this pi cancel. So that's why this is mu naught I by 4 3s are 12, 12r. So B is equal to, this we can write like mu naught I by 4r can be taken common, then it is 1 plus this is 1 by 3. So you will get 4 by 3, 4 4 cancel. So answer is mu naught I by 3r. Okay. Due to this conductor field, here is into, here is out. For this conductor field is here into, here also out. So this conductor and this conductor both are contributing, here field is outward. So I have added. Okay. Otherwise, one is into, another one is out, then we should subtract. Okay. This is the answer. We'll see one more problem. See here, this is a straight conductor carrying current in this direction. This is one semicircular arc, and this is another straight conductor carrying current in this direction. This is point O. Its a radius is r. Previously I have taken loop this side. This time I am bending this side. So current will pass like this. This radius is again 3r, what we have taken previously, the same I have taken. Then we need to find here. Magnetic field B is equal to, due to this is 0. Okay, due to this, actually current is flowing like this. Field here is into, that means here out. Out magnetic field. So that is mu naught I by 4r. We have calculated number of times this one. This straight conductor is again 0. But you see this one, here current is, field is into the board, here it is into the board. So that's why here I am going to take minus. That we got mu naught I by 12r in the previous problem. So this and this are producing magnetic fields in opposite direction. So we have subtracted. Usually the conductor which is close to the point will produce a strong field. This produces weak field. So that's why net magnetic field, this is out, this is into, so outward magnetic field. Here we'll take mu naught I by 4r common, then you will get 1 minus 1 by 3. This we will get 2 by 3. So mu naught I by 2 cancels for 2 times, 4 3s are 6. 6 are magnetic field outwards. This one we'll see. This is a conductor. This is the center of the circular loop. This is radius. This is also a radius, which makes an angle 2 alpha here. Then it is carrying current I. then we need to calculate at point O. So this is very carefully we should do. See here, for this circular loop, it is not a complete loop. If a complete loop is there, then this is the loop. If this complete loop is there, then magnetic field here can be written as B is equal to mu naught I by 2R. Okay, but here complete loop is not there, this portion is not there. So the angle for certain angle mu naught by 4 pi theta I by R is the formula. This angle is not this. This is that angle. This angle we can write it as 2 pi minus 2 alpha. 2 pi minus 2 alpha. So this arc producing magnetic field here is into. So magnetic field due to circular section B1 is equal to mu naught by 4 pi. Theta is 2 pi minus alpha minus 2 alpha into I by radius of the circular loop. This is the magnetic field. This magnetic field here is into. This same current passes here. Due to this straight conductor also it is into. Here we have one arc. Here we have another straight conductor. See, this straight conductor is a straight line. Straight conductor of finite length. Magnetic field due to straight conductor B is equal to mu naught by 4 pi I by R into sin alpha plus sin beta. See this very carefully. When we have a straight conductor, if you want to calculate magnetic field at any point, first we should draw a normal onto a conductor. This normal is x, it is not radius. It is less than radius. Why? Because if arc is there, if extended, this is R, here to here is R, but conductor is ended here, so x is not R. X we should find out. Okay, here total angle is alpha. See, this is radius, this is also radius, so it forms isosceles triangle. So that's why this angle is alpha, this angle is also alpha. Alpha is alpha, beta is also alpha. So that's why I am going to substitute this mu naught by 4 pi I by x, not R, x. Okay, this is also carrying current in this direction, field is into. This is also into, both into. So final magnetic field B can be written as B1 plus B2. Total is also into. Okay, B2 I am calculating mu naught by 4 pi I by R. R is x into sin alpha plus another sin alpha. Okay, now we need to find the value of x. X value we'll find from here. This is R, this is also R. This we have taken x. This is alpha. This is alpha. This angle is alpha. If I want x, I need to use cos alpha is adjacent side by hypotenuse. That is x by R. So x is equal to R cos alpha. Okay now. So the value of B2 can be written as, it is into the board, mu naught by 4 pi I by R cos alpha into 2 times sin alpha. Sin alpha by cos alpha is tan alpha. So B2 is into the board, mu naught by 4 pi I by R into 2 times tan alpha. We should add these two to get resultant magnetic field. So resultant magnetic field B is mu naught by 4 pi 2 pi minus 2 alpha I by R plus this value mu naught by 4 pi I by R into 2 tan alpha. If we take common things, mu naught by 4 pi I by R is common, take it out, then answer will be 2 pi minus 2 alpha plus 2 tan alpha. This is the answer for this question. and here magnetic field is in 2. Like that we can calculate for various combinations. You try few more problems. In any standard book you'll find so many problems like this. So how to do it, method I have told, explain, no, follow this seriously. ಈ ಕ್ಲಾಸ್ ನಿಮಗೆ ಅರ್ಥ ಆಗ್ತೆ, ಈ ಕ್ಲಾಸ್ ನಿಮಗೆ ಇಷ್ಟ ಆಗ್ತೆ, ಕಂಪಲ್ಸರಿ ಸಬ್ಸ್ಕ್ರೈಬ್ ಮಾಡಿರಿ, ಶೇರ್ ಮಾಡ್ಕೊಳ್ರಿ, ಬೆಲ್ ಐಕಾನ್ ಪ್ರೆಸ್ ಮಾಡಿ. ನಾವು ಯಾವಾಗ ವಿಡಿಯೋ ಅಪ್ಲೋಡ್ ಮಾಡ್ತೆ ಆವಾಗ ನಿಮಗೆ ವಿಡಿಯೋ ಬೇಗ ರೀಚ್ ಆಗುತ್ತೆ. ನೀವು ಈ ವಿಡಿಯೋಸ್ನ ಯೂಸ್ ಮಾಡಿಕೊಂಡು ಚೆನ್ನಾಗಿ ನಿಮ್ಮ ಎಕ್ಸಾಮಿನೇಷನ್ಗೋಸ್ಕರ ಪ್ರಿಪೇರ್ ಆಗ್ಬೋದು. ಥ್ಯಾಂಕ್ ಯು.